Hello everyone, I am Sunanta from SNS College of Technology, Department of Mathematics. As the continuation of the lecture series in the topic Numerical Solutions to Ordinary Differential Equation, we are going to see Modified Euler's method in this lecture series. In the previous videos, we have seen Euler's and Taylor series methods. So this modified Euler's method is an improved version of an Euler's method, and this method is also known as improved Euler's method or Hume's method, in which we are approximating the solution to first order ordinary differential equation. This technique that enhances the basic Euler's method by averaging the slopes at the beginning and to the end step. So it is a second order Runge-Kutta method and provides better accuracy than the Euler's method. So now let us see the procedure for this method. So in this method, first we will use to predict value, next correct, and we will do the iterations. So first a predictor step is taken similar to the basic Euler's method to estimate the solution at the next point. Next the corrector step that refines the estimate by using the average of the slope at the current point and then the midpoint between the current and the next point. Next is an iteration procedure, so it will be repeated again and again. Next, improved accuracy. This modified Euler's method is generally more accurate than the Euler's method, especially with large steep sizes. That is, when the h value is taken large, then we can use this modified Euler's method to find the solution with better accuracy. Next is relatively simple. So this method is comparatively relatively simple to the Adams fourth method and Millen's method and all. Next is the second order accuracy. So the error in the modified Euler's is also proportional to h square, and modified Euler's method offers a good balance between accuracy and simplicity for solving first order ODE equations. It provides a more refined estimate of the solution than the basic Euler's method by incorporating an average of slopes over the interval, resulting in more accurate approximate solutions for the curve. So the next comes to the error analysis. Here the error analysis will be equal to O of h3, h cube, which is here the order is power 3, therefore it is O of h, order of h3. Next is comparison with Euler's method. So this method is more accurate compared to the Euler's method, and computational is slightly heavier due to the formula. Next comes to the advantages and disadvantages. So this is more accurate than basic Euler. Next, it still simple to implement. Next is the disadvantages. This is comparatively slower than the Euler's method because of the formula, predictor and corrector formulas. Next is this is not that much accurate to the Runge-Kutta method and all. So here let us see when to use in Euler's method. So when we need a better accuracy than the Euler's method, we can use this modified Euler's method. And when non-stiff ODEs where Runge-Kutta method might be overkill. Next is in an educational context to introduce predictor and corrector methods. Next is for the similar methods are Runge-Kutta fourth order method and adaptive steep size methods can be used to the similar problems which can be solved using a modified Euler's method. Now let us see a problem based on a modified Euler's method. Before getting to the problem, let us see the formula for modified Euler's method, which is given by yn plus 1 is equal to yn plus h of f of xn plus h divided by 2, comma yn plus h by 2 into f of xn, comma yn. Now we are going to consider a problem y dash is equal to 2xy with y of 0 is equal to 1, and we are asked to find the x value 0.25. Now from the given conditions we can take the value of x0 is equal to 0 and y0 is equal to 1, and h is equal to x1 minus x0, which is 0.25 minus 0, which can be given as 0.25. Next, let us find f of x comma y, which is 2xy. So which of f of x naught comma y naught can be given as 2 into 0 comma y, which is 0. Next is by modified Euler's method, yn plus 1 is equal to yn plus h into f of xn comma h by 2, yn plus h by 2 into f of xn comma yn. Next we are going to apply n is equal to 0 here. Therefore we will get y1 is equal to y0 plus h value 0.25 and f of x0 plus h divided by 2 comma y0 h by 2 into f of x0 comma y0. So here our y0 value is equal to 1 and h value is equal to 0.25. f of x0 value is again 0, h value is 0.25 divided by 2, y0 value is 1 plus h value is 0.25 divided by 2 into our f of x0 comma y0 is calculated as 0. On applying that we will get 0. On simplification we will get 1 plus 0.25 into f of, so on simplification of this we will get f of 0.125 and adding this we will get 1 plus anything into 0 will be 0. So f of 0.125 into 1. So on calculating f of 0.125 comma 1 we will get 2 into x value is 0.125, y value is 1. Therefore our value is 0.25. On applying this in the given thing we will get 1 plus 0.25 into 0.25, which in turn gives the result 1.0625. This is our y1 value for x is equal to 0.25 by our modified Euler's method. Thank you.